I think this is a good time to begin. So I guess I'm going to become the first one in the summer school to actually complete my lectures in about an hour and a bit. So may I reiterate what a great pleasure it is. So this lecture is the third one in my series, and it's the one that I've promised you on topological insulators. And it's the one that's going to connect with everything that we've done so far. So I'll remind you that in the first lecture we looked at semi-classical wave packet dynamics and the Boltzmann equation. And in the second lecture we looked at K.P theory and the spin-orbit interaction and how to get a finite Berry curvature in the Rashba model. So in this lecture I will give an introduction to three-dimensional topological insulators. So really TIs are of two kinds. Roughly speaking, there's a three-dimensional version, there's a two-dimensional version. They're very closely related. So I will focus on three-dimensional topological insulators. And I will actually derive their surface states. Then I will look at topological insulator films and what happens when there is tunneling between the two surfaces. And then I will finally conclude with my own understanding of the quantum anomalous Hall effect. So hopefully I can give you a simple rule of thumb sort of understanding that you can take home and meditate about. And I was planning to spend a fair amount of time on the edge states, but I've boiled all of that down to one slide. And I think by the time I get to that slide, it will be obvious why I've made this choice. And that also connects with a discussion that I was having with Michael just a couple of days ago, relating to the difference in the edge states between the quantum anomalous Hall effect and the quantum Hall effect. And then to conclude, I'll just ask, I'll tell you a couple of things that are related to this question, whether transport is really dissipationless in these systems all the way. So I think in the first lecture I told you that if you wanted to understand wave packet dynamics, you should read the paper by Sundaram and Neal. Then if you want to understand K.P theory and most of solid-state physics, you should read Marder's book. If you want to understand topological insulators, you should read this book by Shunqing Shen, who's one of the leaders in the field. He's a guy I talk to quite a lot. I'll be referring to this book quite a bit throughout this lecture. So before we go into the equations, I want to ask the question, what is a topological insulator? So the way I think of a topological insulator is as a material that is a little bit schizophrenic. So part of it wants to conduct and part of it doesn't want to conduct. So there's a two-dimensional version, which is a system that consists of an insulating surface. But the edges of this surface are conducting. They are chiral, so the spin is locked to the momentum. It's actually perpendicular to the momentum. So I will show this in detail later on. So they're chiral, and the states, so each state has a definite spin orientation. There's also a three-dimensional version, so 3D topological insulators. That's what I have spent most of my time on. So that consists of a three-dimensional insulating bulk and a series of conducting surfaces, and again the surface states are chiral, and each state has a definite spin orientation. Now you may be aware that nature has given us quite a few insulators, so quite a few kinds of insulators, and it turns out that all of these can be topological if spin-orbit coupling is large enough. So we have the most boring kind, which is a band insulator, which just so you have a conduction band, a valence band, they're separated by an energy gap, right? The distinction between a semiconductor and an insulator is actually, to some extent, is arbitrary. So at finite, if the gap is larger than it's much larger than room temperature, then you get no carriers in the conduction band. That's a band insulator. Right? You have a gap, but you have a finite number of carriers excited into the conduction band at room temperature. That's a semiconductor. So that, of course, will become a topological insulator when spin-orbit coupling is strong enough, as I'm going to show. Now, there's also an Anderson insulator. So an Anderson insulator, so that's a result of Anderson localization. And Anderson localization is the So it's a strong case of what we know as weak localization. So Michael has touched upon that yesterday, and I think he's going to go back to it in his next lecture. But essentially what happens is when scattering is strong enough, there is this, in quantum mechanics, you can always backscatter to where you came from. Right? And if you have, let's say, an impurity, you go around the impurity, you come back to where you came from, you can do this in two ways. Right? And these two paths are time reversed. So, in classical mechanics, you just add them. In quantum mechanics, they interfere. Right? And this interference gives rise to a reduction in the conductivity. So weak localization generally results in a reduction in the conductivity. When you have a lot of impurities, you get more and more weak localization until the conductivity goes all the way down to 0 and the system becomes an insulator. So that's an Anderson insulator. So an Anderson insulator, as actually Shunqing Shen showed, can also become a topological insulator. There's also a Mott insulator as a result of strong electron-electron interactions. So you can think of this in terms of a two-atom picture. So how does conduction occur? You can think of conduction as occurring by hopping. And then if the electron-electron interactions are very strong, then the Coulomb repulsion, the on-site Coulomb repulsion, is going to prevent electrons from tunneling from one atom to another. And then the system is going to become an insulator. That's called a Mott insulator. Incidentally, to the best of my knowledge, Anderson and Mott both got the Nobel Prize in 1977 for discovering these interesting kinds of insulating behavior. And there's also a Kondo insulator where you have, let's say, a magnetic impurity and a large Fermi C, and at one point the conduction electrons hybridize with the states on the impurity in such a way that the impurity mediates interactions between the conduction electrons, which are otherwise not interacting, and these combine into a large-scale sort of macroscopic state that has a singlet orientation, and eventually the system, likewise by hybridizing with the impurities, also becomes an insulator, so which we call a Kondo insulator, and we have one of the people that is discovered, that's responsible for the discovery of the topological Kondo insulator, Viktor Galitsky, and I think he's going to be talking right after me. So all of these will be topological insulators if spin-orbit coupling is strong enough. And just to give you a, to complete the overview, you may be aware of how a superconductor works. So in a superconductor, because let's say in a BCS superconductor, because of the electron-phonon interaction, you open a gap at the Fermi energy. So anything with a gap behaves like an insulator. So a superconductor can also become a topological superconductor if the spin-orbit coupling is large enough, except the carriers, so the quasiparticles will be the Cooper pairs, right? So I certainly won't be talking about topological superconductors, but people who are looking at Majorana fermions are spending quite a bit of time on this. Now, so a couple of days ago, when I was talking about the Berry phase, I told you that one of the early examples of the Berry phase was the Aharonov-Bohm effect. And of course, Aharonov and Bohm didn't actually know that their effect was an example of the Berry phase. So the very first example of a topological insulator was the quantum Hall effect, so a quantum Hall system. Of course, Klaus von Klitzing et al. Did not know that what they had was a topological insulator. So in essence, a quantum Hall system is a two-dimensional topological insulator in the sense that we have no bulk conduction, so we have no, at certain points, we have no conduction throughout the sample, but we have conduction due to certain edge states. And the reason this is topological is, as Michael pointed out a couple of days ago, you have, so this is your sample, this is one edge, this is the other edge, this edge travels this way, this edge travels this way, and you can't scatter because so on this edge you can't backscatter because there's no states to go to. If you want to travel in the other direction, you need to scatter all the way to the other side of the sample, right? So I'm just reviewing this basic concept. So as a result, the whole conductivity turns out to be quantized. So it's some number, actually the number of Landau levels, times the conductivity is quantum, E squared over H. So I guess most of you will know that the quantum Hall effect these days is used. I have one, but I like the old-fashioned sort of, right? So the quantum Hall effect is used as the international standard of electrical charge, right? So N, it was later discovered, is what's called the topological invariant. So whatever deformation you make to your system, N is going to remain the same. And it's actually, it's directly related to the Chern number. And the Chern number is nothing but the Berry curvature that we talked about, integrated over the entire Brillouin zone. So you can prove that that is equal to an integer. And in physical terms, you turn on a magnetic field, you have Landau levels, you also have a Fermi energy, which tells you how high up in energy you can be, and this N just counts the number of Landau levels underneath the Fermi energy. Now, obviously, because of the magnetic fields, the quantum Hall effect breaks time reversal, and the current generation of topological insulators is time reversal invariant. So this is this is all I want to say about the quantum Hall effect. So again, before I go into the algebra and the complicated sort of lattice figures, I'll just make another another set of general observations. So strictly speaking, in a topological insulators, for various technical reasons, you can't really talk about a Chern number. So how do we identify a topological insulator? We need to come up with another kind of invariant. So Kane and Millay came up with this thing called a Z2 invariant. And for all intents and purposes, Z2, so the 2 just means 0 or 1, right? So Z2 just means 0 or 1. Now, how do you calculate this? In general, this is actually a very complicated problem. So the key thing in the current generation of topological insulators is time reversal symmetry. And this kind of hints at the fact that you might want to have something to do with the time reversal operator, right? Which is just I times sigma y times the complex conjugates, right? Just in case. So what you need to do is, first of all, you take your crystal, you take the band structure of that crystal, which consists of an infinite number of levels, right? You'll want to truncate that at some point. You take the time reversal operator, and you create an immense matrix containing all the matrix elements of the time reversal operator, right? And then from those matrix elements, I think you have to find the determinant, the Pfaffian or something. I don't actually remember exactly off the top of my head. You take that matrix, you find something that's like the determinant, and at the end of the day, that will give you 0 or 1. Right? And that's your topological index. If it's 0, it's boring. If it's 1, it's a topological insulator. Right? And again, this Z2 invariant counts the number of, essentially the number of Dirac cones on the surface. If it's 0 or even, then it's boring. If it's 1 or it's odd, then it's not boring. So, so for a topological insulator, basically, you know, the sort of basic sketch is you have the conduction band, you have the valence band. Obviously, you want, this is for the bulk, for the 3 dimensions, you want to be in the gap. Right, and in the gap you have a pair of surface states which cross, right? People usually just draw it as an X in the middle of the gap. The location of this crossing is not topologically protected. So you can be close to the conduction band, you can be close to the valence band, right? So this is just a simple basic sketch. And this is what happens on one surface of a 3-dimensional topological insulator. This is what these states look like. And this is as a function of momentum. There's a theorem which is called the fermion doubling theorem, which says that fermions come in pairs, right? And where is the pair of these states? Again, we have to resort to physics. This is a 3-dimensional system. So if I have one surface that's topological, so if I have the top surface that's topological and has a Dirac cone, there's going to be a bottom surface which is going to have a similar Dirac cone. Okay, so one more thing. Think of the sample. So it's a top surface, a bottom surface, and basically a slab, right? And if the top and the bottom have topological states, then the sides also have topological states, right? So also have Dirac cones on them. That's going to become very important at the end of this lecture. So I'm going to reiterate this, but it's going to become very important when we're looking at Hall transport. So the material that has been studied, say, most commonly in the context of three-dimensional topological insulators is bismuth selenide, which is a relatively complicated material. So it is composed, so this is from one of the seminal papers, this Nature Physics paper from 2009, by a group in China, Haijun Zhang, and a number of people at the Institute of Physics of the Chinese Academy of Sciences. So this is, a snapshot, sort of a cross-section, sort of a view of the lattice. And what matters, that the figure we should focus on is here. So this consists of quintuple layers, so 5 at a time, right? So we have A, B, C, A, B. This is not the unit cell, but this is still an element that we can sort of not reproduce. What's the word I'm looking for? Repeat in order to generate the whole lattice. It's not the most basic unit cell, but it's the recursive element, right? So we have selenium, bismuth, selenium, bismuth, selenium. These are called 1, 1, 1 prime, 1 prime, and then the selenium 2 layer. So selenium 2 acts like a center of inversion. So a selenium 1 is equal to selenium 1 prime. That's why they're drawn in green. Bismuth 1 is equivalent to bismuth 1 prime. So this layer, the selenium 2, plays the role of an inversion center. So when you apply the spatial inversion operator, you map bismuth 1 into bismuth 1 prime, selenium 1 into selenium 1 prime. Because you have inversion, the eigenstates have definite parity, right? Why am I doing this? So there's a couple of so inversion symmetry is important for a number of things that I'm going to say from now on. And also I wanted to sort of get across the idea that even though when you look at this figure, you're asking like, what on earth is this? There are actually some underlying symmetries even in this incredibly complicated structure. So the structure is ever so slightly a non-Bravais lattice. So I'll remind you that a Bravais lattice has 1 atom per unit cell. Bismuth selenide has 5, right? So to the best of my knowledge, if you want to do tight binding for bismuth selenide, I think it's going to be relatively computationally expensive. That's at least until we discover topological quantum computing, and then there will be no problem. So, so how do we describe bulk bismuth selenide? I'm really following the following the discussion in Shen's book. So at this point, this is still kind of introductory. So if at the end of this slide you're not entirely sure about the structure of the atomic levels, you can sort of don't feel too guilty. So I'm going to give you the explicit model in actually on the next slide, the model that we need to worry about. So let's start from the atomic energy levels, right? We want to build up a simple model for the band structure, and essentially we're interested in the energy eigenvalues at the gamma point. So the gamma point is just the center of the Brillouin zone, and that is where the minimum of the conduction band and the maximum of the valence band are. So we want to ask, this material has a strong crystal field, and of course, it has a strong spin-orbit interaction. Like I told you yesterday, the materials that we'll be interested in will have a strong spin-orbit interaction. So what do these things do to the atomic levels, and what repercussions does that have onto the band structure? So it turns out, band structure people tell us that near the Fermi surface, the states that are relevant come from p orbitals. And as it turns out, both bismuth and selenium have an atomic structure with p orbitals, so 6s2, 6p3, 4s2, 4p4, so both of them have p orbitals. These are degenerates, but once you add the crystal field, that removes the degeneracy. The only thing that's left are the lowest lying orbitals are the pz orbitals, and that's related to the point group symmetry of the crystals. So bismuth, right, you have PZ1 plus, that's higher in energy. In selenium, you have something that's PZ2 minus, so I'll actually define these on the next slide, because we're going to be using them in the, to describe the band structure, so I thought I'd save the definition for the next slide. So forget about what 1 and 2 mean right now. Plus and minus just tell you how they change under parity. There's an energy gap between these orbitals, right? And this energy gap is controlled by the spin-orbit interaction. So even at the atomic level, right, when you increase the spin-orbit coupling, which is what I'm doing in going from left to right, you will actually cause a level inversion, right, inside the atom. If you could, right, change the spin-orbit interaction inside the atom. So this is kind of the clue that tells us how we get this, that sort of hints at why there is a level crossing, or rather, sorry, a band crossing in the actual crystal itself, or a sort of band inversion, which is essentially what these surface states are, because the surface states connect the conduction band to the valence band. So, so that was the bulk. So I'll give you the model now. I just want to point out that even though this is not always written in the specialized literature, the Z direction here corresponds to the 111 axis of the crystal. So it's not one of the main crystal axes, 100, 010, or 001. So the PZ orbitals that we want to worry about, so they're called P1Z plus. Obviously there's up and down, P2Z minus. So 1 labels the bismuth, 2 labels the selenium. Plus or minus just represents the parity. Obviously, up and down just represents spin. So I'm justifying this notation. For us, they're just going to be the basis sets of a matrix. So using these states, we can construct this K.P Hamiltonian, which the band structure people have kind of kindly done for us. So I just wanted to point out, before we look at it in detail, that this actually looks very much like the Dirac Hamiltonian. So what did the Dirac Hamiltonian look like? We had a sort of a mass term with opposite signs. So we had so it's a 4x4 Hamiltonian. We have, it's made up of 2-dimensional blocks, right? Mass minus mass, sigma dot momentum on the off diagonal. This has basically the same structure. Something that looks like a generalized mass, something that looks like minus a generalized mass. We have this P term, which is essentially an offset, so that comes from the bulk band structure. And on the off diagonal, we have these sigma dot P terms, which I've decomposed into sort of an in-plane part and an out-of-plane part. I'm sorry, I've missed out an H bar over here. So V parallel refers to Vx and Vy. V perpendicular refers to Vz. X and Y, if you recall the lattice structure, this is a layered material, and the interactions within the layers are much stronger than the interactions between the layers. So this is why this symmetry decomposition exists between X and Y, which is within one layer, and Z, which is between layers. Okay, so we have essentially a Dirac-like equation. There's a term in the energy which breaks the particle-hole symmetry of the system. I'm giving you this mostly for completeness. The reason there is a p-linear term is because if we look at the basis functions, we see that the bismuth orbitals are even under parity, the selenium orbitals are odd under parity. So because of this even-odd alternation, we are allowed to have p-linear terms in the band structure in very much the same way that we were allowed to have linear terms in the Rashba Hamiltonian when we broke inversion symmetry. And just to make sure, in this model there's no magnetization, so the model is time reversal invariant, as expected, because there is no magnetization in the system. So here, for example, h bar and v remain unchanged when I apply the time reversal operation. Sigma changes sign, p changes sign. So the overall thing, the overall quantity does not change sign. And you can apply the same considerations to all the other terms in the Hamiltonian. So now we're starting to get close to the more exciting aspects of the problem. So we have some sort of a Hamiltonian to describe the bulk, or at least the relevant part of the bulk. And once we have the bulk Hamiltonian, we are able to derive the surface states. Because, so the way this works is as follows. So we take the Hamiltonian from the previous slide, so that's a k dot p Hamiltonian. That's for an infinite periodic perfect system. And now we say we're going to look at the surface, so we obviously have to cut off the system at some point. So we're going to say, let's do this at z is equal to 0. In the xy plane, there is no change. We still have translational invariance. So px and py are still good quantum numbers, but pz is not a good quantum number because we're breaking translational invariance in the z direction. So we have to take that Hamiltonian, we have to set pz equals minus ih bar ddz. Remember, we're doing k dot p theory, so here I'm actually using the momentum rather than the wave vector. But these p terms, I'll remind you, we are close to the band edge, so the momenta are going to be small. So the first thing we do is we replace pz as minus ih bar ddz, then we set px, py equal to 0. So that will give us the solution, that will give us a matrix Hamiltonian with a series of differential operators. Maybe I should also justify this. Before I go on to solve this, I should also justify this on physical grounds. So you may be asking, maybe k dot p theory is too fresh in your mind, and you may be asking, why should we set px, py to 0? Well, so px, py will be on the order of the Fermi wave vector, whereas pz is going to be much larger due to the confinement. So pz, the magnitude of pz is going to be 1 over the confinement. Right? The confinement is going to be on the order of 1 nanometer, right? Which is going to be much, much larger than any kf that you'll be able to get when doping this. So we are safe on, from basically all points of view. So we take this Hamiltonian, we get a bunch of d squared dz squareds on the diagonal, and we get a bunch of ddz with sigma matrices on the off diagonal. Because we have this EP term, which breaks the particle-hole symmetry, the equations are just a little bit more difficult to solve, but they are very tractable analytically, as I'm going to show on the next slide. And I'll just tell you that in this particular model, for d perpendicular magnitude greater than b perpendicular, the system is no longer an insulator, so we're just going to focus on d perpendicular less than b perpendicular. That's not to say we can't find some solutions in the other case. They're just not of interest to us. And when you take the numbers from the band structure, certainly this holds. So I didn't have space to write the entire Hamiltonian in all its beauty, but you'll see that this guy goes as the identity matrix. So the identity matrix has a couple of zeros on the diagonal. This goes as sigma z, right? Sigma z also has a couple of zeros on the off diagonal, right? So if you have the matrix structure in your head, and you're not to be blamed if you don't, you may sort of realize that you can decouple rows 1 and 3 from rows 2 and 4, right? So you can boil down this 4x4 matrix differential equation to two 2x2 matrix differential equations. So because of this, we can take two trial solutions. One of them is going to be e to some exponential, so we want states that are localized near z is equal to 0. This exponential is going to turn out to be negative. Right? one finite matrix element, so one finite element, A1, and another finite element at number 3, B1, and exactly the same thing for the second matrix, for rows 2 and 4, except now we have A2 and B2 as the second and the fourth elements. So we have two independent sets of equations. So it's a matrix differential equation, but it's only ddz and ddz squared. So those act on the e to the lambda z. They give you a matrix of this form. They give you a very similar matrix for the second wave vector, right? So A2 and B2. And now these become straightforward eigenvalue equations, which you can both solve the same way. So then you go and do your high school textbook, determinant of the matrix minus the energy eigenvalue is equal to 0. I'll just point out, because we have a ddz squared, that will give us a lambda squared. So lambda squared here. So at the end of the day, we have a quartic in lambda, right? However, two of the solutions are going to be, so they're going to be exponentially increasing. So obviously we throw them away. We want to impose this condition that the wave function vanishes at the interface, and it also vanishes as you go infinitely far away from the interface. So you get localization at the interface. And then the wave function simply takes the form. So once you work out your solution explicitly, so it takes the form e to the lambda 1z, e to the minus lambda 2z, right, times this wave vector. It's exactly the same thing. So it's exactly the same thing for the second solution. I didn't bother to write out the exact coefficients, the exact exponents, normalization factors, and so on, because I don't think anybody would be making any sense of it in here. So I would just suggest look those up in Shen's book, or if you don't want to do that, I can just prepare an extra slide and add it on to the presentation. So these are now, right, so the lambda 1s and the lambda 2s are negative, so these things actually decay when you go away from the interface. And what you want to do now is, remember, we've set px and py equal to 0. So now we have to restore them. We have two basis states, psi1 and psi2, that we have just worked out. So we now want to add the px and py terms in the Hamiltonian. So that means we take psi1 and psi2, and we take the Hamiltonian complete with the px and py terms, and we have to calculate the matrix elements psi1h psi1, psi1h psi2, the complex conjugate, and the second diagonal element. Obviously, these are just going to give us so something that goes as the identity matrix. So we get an offset, we get something that goes as p squared, that I'll talk about in a minute, so p in plane squared, and then lo and behold, we get, again, I missed out an h bar, so we get a prefactor, sigma xp, oh, I didn't miss out an h bar, it's in the p's, sorry. So sigma xpy minus sigma y px, which, as we anticipated yesterday, is nothing but the Rashba Hamiltonian. How is this different? Yes, Cedric.
So you restore the px and py. Does it mean you do it in perturbation, or treat them as perturbation?
It is a perturbation, and now it's a perturbation with respect to pz, because pz is large, right? And it's large because of the confinement, right? So E0 we can just forget because it's an offset. This d parallel, it's important for topological reasons when you calculate Chern numbers and so on. But we actually did a very primitive trial calculation all the way back when I was in Maryland, and it turns out that this term only becomes significant at densities larger than 10 to the 14 per centimeter squared. So that you cannot even get in graphene. That's so large that you can't even get it in graphene, so we don't need to worry about that. So essentially, the difference between this system and an ordinary Rashba spin-orbit coupled semiconductor is that we can just about forget about these identity matrix terms, and Rashba is everything, right? This is why the dispersion looks like this, right? It's a cone rather than two spin-split bands, as I showed in yesterday's lecture. So because of this, the chemical potential is going to be, let's say, somewhere over here. So there's only going to be one Fermi surface, and there will certainly not be any spin precession because there is only one set of states at the Fermi energy. To get spin precession, you need to have at least two energy eigenstates because you need to be the spin to be changing between two energy eigenstates. So even though it looks like Rashba, there are some serious physical differences between this system and a Rashba system, or Rashba semiconductor. So this is a good point to review a basic but important bit of terminology. Actually, three basic but important bits of terminology. So let's first look at what the Fermi surface looks like. So as I pointed out yesterday, this Rashba Hamiltonian looks like an effective magnetic field that is just changing as a function of wave vector. So the effective magnetic field is just these red arrows. What happens to the spins? Well, in equilibrium, the spins, which are the green arrows, are just going to be following the direction of this effective magnetic field, because that's the only thing that the Hamiltonian lets them do. So the direction of the spin is completely set by the direction of the momentum, and the technical jargon for this is that we have spin-momentum locking. In this case, obviously, so let's say over here, the momentum is going to be pointing in the radial direction, whereas the spin is pointing in the tangential direction. So the direction of the spin is perpendicular to the direction of the momentum. So we say this system is chiral. Now, if you were doing this in a mercury telluride quantum well, you'd be doing a very similar kind of analysis, K dot P analysis for the surface states, and you'll be finding out that the Hamiltonian has very much the same form, except it's sigma x kx plus sigma y ky. So now you'd still get an effective magnetic field at each point in k space, except it would be pointing radially rather than tangentially. So the spin is still locked to the momentum, but it will be parallel to the momentum. So then we say the system is helical. Now, you can always rotate one into the other because you can always just rotate your wave vector, right? So you can always just redefine your wave vector. So I take the Rashba Hamiltonian, I take kx to ky, let's say I take this Hamiltonian, I send kx to ky to minus kx, I immediately end up with Rashba, right? So the point is, no matter what it looks like, the physics is always the same. And from the point of view of the Berry curvature, anomalous Hall effect, etc., the physics is always the same. Graphene is very similar. You don't get a quantum anomalous Hall effect in bare graphene because the sigma that appears in graphene, so it's sigma dot k, is actually not the spin. It's something else. It's related to this sublattice pseudospin that Michael was talking about. And again, it's related to the fact that the lattice is non-Bravais. It has 2 atoms per unit cell, so these are not equivalent. All right, so yet another bit of basic physics that is now very easy to understand once we know that everything is Rashba. So when you sort of transport electrons, and when electrons are moving throughout the crystal, they scatter off impurities. And in principle, in quantum mechanics, as we already discussed, you can also scatter back, in the direction opposite to the one you came from, right? So that, unsurprisingly, is called backscattering. So what happens if we try to backscatter in a system like this? Suppose I'm here, right, and I want to backscatter to this point. What must happen to the spin in order for this to happen? Right? The spin must flip. And in order to flip the spin, I need something that breaks time reversal. So ordinary Coulomb scattering cannot do this. Roughness, short-range scattering cannot do this. Right? So this is why backscattering is prohibited. So this is the sort of intuitive, or as I would call it, the hand-waving explanation. Okay? Now, you can also prove it formally. right? You take the Rashba Hamiltonian, and in 2 minutes you find the eigenstates. Remember that in K.P language, these play the role of those U's, so I'm going to call them U. So the eigenstates actually don't depend on K, they depend only on theta, which is the polar angle of the wave vector, and then one of them is -1, the other one is +1. I can't remember which one is particles, which one is holes, right? So in Fermi's golden rule, right, so the scattering time is given by Fermi's golden rule. So at each point k, so suppose on the Fermi surface, I have to sum, so I have a phase space factor, then I have a sum over all the other wave vectors, k prime, right, that I can scatter to, and then I have a matrix element between the initial state at wave vector k, the final state at wave vector k prime, and the disorder potential, right, or the phonon potential, or whatever. So deformation potential, whatever. This is squared, and then I have elastic scattering because the energy at k must be equal to the energy of wherever I'm scattering to at k prime. So I guarantee you that when you take this and you put in the Rashba eigenstates, so one of them will have e to the minus I theta, the other one will have e to the I theta prime, and you will end up with a factor of 1 plus cosine theta minus theta prime, right? So when theta prime is equal to minus theta, that's basically scattering by pi. Cosine of pi is equal to -1, right? So 1 plus -1 equals 0. So that tells you that the amplitude for scattering from k to minus k is exactly 0, formally. And this, incidentally, is also what people refer to as topological protection against weak localization and, in the stronger case, against Anderson localization. So there is an argument that if you have a... Yes?
Maybe it's theta prime equals pi plus theta.
Oh, it should be pi plus theta. Yeah, apologies. So thanks. All right. So there is an argument that if you have a topological insulator and you add disorder to it, this will not turn to an Anderson insulator. So this is just an aside. So let's talk about some other interesting things that happen in a topological insulator. So the Hamiltonian is of the Rashba form. So here I'm going to give you simply a formal explanation, and then on the next slide I'll give you a physical explanation for what happens. So the Hamiltonian is basically the spin dot the wave vector. What is the current operator? The current operator is just the velocity operator, and the velocity is just dh dk, right? This Hamiltonian is spin dot k. So when I take the velocity operator, so I take dh dk, I get something that is directly proportional to the spin, right? Which tells me that whenever I have a current flowing in the sample, right, I necessarily have a spin polarization that accompanies that current. And this again refers only to the surface of the sample. So you get a spin polarization that exists throughout the surface. You don't get it in the bulk, because the bulk, as we just discussed, has inversion symmetry, and you can immediately prove just by looking at, you write down a sort of Ohm's law type relationship between the spin and the electric field, and you can immediately see the spin doesn't break inversion, the electric field breaks inversion, so whatever goes in between the two must also break inversion symmetry. So it can't happen in the bulk of the sample because the bulk has inversion symmetry. So if you do see a spin polarization, it will be there purely because of these surface states, and it will be a signature of surface transport and a smoking gun for this topological insulator Rashba type behavior. This has actually been detected. So I was looking for it's a famous Nature Physics by Dan Ralph, published about 2 or 3 years ago, right? So I forgot to put in the reference, so I'll have to dig that up when I go back. So how does this happen physically, right? Physically, if you have no electric field, this is exactly the figure I was showing before. So you have this spin orbit effective field, and the spin's just following it in equilibrium. Now, when you apply an electric field, you're shifting the Fermi surface away from its equilibrium position. So now everything is defined not from the center of the circle, but from this shifted location. In the direction parallel to the electric field, nothing changes. In the direction perpendicular to the electric field, you see that we acquire a net. So essentially, we generate a net spin orbit effective field, and then perpendicular to the electric field, and then the spins actually have to follow this. So certainly, there's a large component of the component of the spin actually follow this. So this is the physical explanation for why there is a spin polarization in response to an electric field when you have this spin momentum coupling that comes in through the Rashba Hamiltonian. So let's now move up a gear and start heading towards the anomalous Hall effect. Still no magnetization, no magnetic field. But we need to start worrying about what happens when we take a real sample. And I'll remind you that a real sample has two surfaces. So this is the slab, this is the top surface, and this is the bottom surface. Now, we need to find the surface states for this structure, and we can no longer get away with solving the so Schrödinger essentially K dot P equation for a single surface, because this film might be thin and the surfaces might communicate, right? But the procedure is extremely simple. Once you've calculated the states for one surface, the procedure is very simple, right? So you take the Hamiltonian, and instead of just cutting it off at one surface, you cut Z off at 2 points, so Z top and Z bottom, right? You end up with exactly the same equations, except the boundary conditions are now a bit different, right? And you no longer throw away you get 4 solutions for lambda, and because the system is no longer infinite, you don't get to throw away 2 of the solutions. So you just have to do more algebra, but you end up with something very similar. Now, this results, obviously, if the film is thin enough, the wave functions for the two surfaces will have some finite overlap. So there will be some noticeable tunneling between the top surface and the bottom surface. And people have calculated this, and they figured out that this is important if the film is ultra thin, so basically less than 5 nanometers, and certainly very important if it's on the order of 3 nanometers. This scale should not be a surprise, because the size of the wave function, the extent of the wave function for a single surface is around 1 nanometer, right? So once the separation becomes of the order between the surfaces becomes of the order of a few nanometers, then the wave function overlap and tunneling is going to become important. But we don't need to do all that algebra to figure out what the Hamiltonian will look like, because we can just write it down by hand. So we know that it's obviously going to be 4 by 4, because we have 2 surfaces and each of them has a spin-dependent Hamiltonian. So I'm going to get a Rashba Hamiltonian for the top surface, and I'm going to get a Rashba Hamiltonian for the bottom surface. So because of inversion, it's actually minus, right? But the structure is exactly the same. And then let's ask ourselves, what is the basis in which we write the Rashba Hamiltonian? So we write spin up here, spin down here, right? Then spin orbit couples spin up to spin down. Likewise, this is spin up here and spin down here. So when I get tunneling between the top and the bottom surfaces, that will certainly not break time reversal, right? So I can only tunnel from spin up to spin up and spin down to spin down. So I go from spin up here to spin up here, that's T, and there will also be tunneling from spin down to spin down, which is also T, because these are entirely equivalent, right? And then we just have, these are usually real, so we just have, exactly the same thing on the, so across the diagonal. Now, it's very simple to diagonalize this, and now you'll get that the energy eigenvalues are twofold degenerate. They're twofold degenerate because we still have time reversal symmetry in the system, so we must have Kramer's degeneracy. The formula is very simple, so square root of Rashba energy squared plus tunneling squared. The key difference, which I'm going to come back to in a few slides, so the main difference is that in the case when the tunneling is strong, right, the electrons no longer live on the top surface or on the bottom surface, right? So if I apply an electric field, transport involves electrons from both surfaces concomitantly, right? So it's no longer legitimate to talk about a spin living on the top surface and a spin living on the bottom surface. At the same time, right, if we look at this Hamiltonian, or these energies rather, in the asymptotic, in two asymptotic limits, those are also very simple to understand. So let's suppose that t is small, right? Suppose t is negligible. So tunneling is negligible. Forget about this thing. I get the square root of a square, which is just Vp, right? That's just a linear spectrum, so it's just Rashba, which is what we expect, right? What if tunneling is very strong? So tunneling is much larger than this Rashba energy. Then I take the tunneling so I do perturbation theory with respect to this thing. So tunneling is the large term. I expand this square root. The first term in the expansion is going to be p squared, right? And p squared, scalar, right, is just like an ordinary boring semiconductor, right? So those are the two limits that a film.
Does it impose some sort of physical limitation to a small component? Like, so you can't have it as small as you want.
So a small.
In terms of size.
You can get down, so people have got down to 3 nanometers as far as I know.
And
that's
being saved from being dominated by tunneling.
Yeah, so there's other problems there. There are other technical, like material science problems in topological insulators. So the surfaces are pretty rough. Okay, so once you bring two of them together, yeah, all hell breaks loose, essentially.
Tunneling is not the limitation.
Sorry? Tunneling is not the limitation. There's still material science issues that have not been overcome. All right. So let's take a film which may or may not have tunneling, and let's make it magnetic. Okay, so we add a magnetization parallel to Z, so perpendicular to the two surfaces. This is the setup that I have in mind. So as these guys, it's the figure I took from this review on the archive. So it's Shojan Jan's group. Strong topological insulators at the top surface, bottom surface. You put a ferromagnet on top, you put a ferromagnet on the bottom, and you make sure that the magnetizations of these two ferromagnets point in the same direction. So because of this so-called proximity effect, when you put a ferromagnet on top of some other material which is non-magnetic, some of the magnetization leaks into this sort of topological insulator. So in a small region near the interface here, in a small region near the interface here. So this is called the proximity effect. Intuitively, it's quite sort of simple to visualize. Now, we have a magnetization that couples to sigma z, so that's basically a Zeeman term. So that will have exactly the same form for the top and the bottom. So I'm going to stick with the thin film Hamiltonian. I have tunneling here, Rashba here, minus Rashba here. Now I have a magnetization which gives me, so couples to sigma z, so M minus M, M minus M. Right? Is everybody happy with this? Good. So the one thing we need to do now is we have those T's on the off diagonal which look inconvenient. So we want to rotate our basis functions in order to get rid of these off diagonal blocks. So I worked it out yesterday and it works. So this is the recipe. So these are real. You get a bunch of zeros on the off diagonals. So it's actually very simple to take care of this. You just take linear combinations of bonding and anti-bonding, and you end up with this this is interesting. So obviously the Rashba terms will not change. Actually, yeah, so that the P plus and P minus are inverted. That doesn't matter. So, so for all intents and purposes, the Rashba terms don't change. You end up with two blocks. In the top block, you have the magnetization renormalized by tunneling, and a magnetization, so minus the magnetization renormalized by tunneling, minus magnetization plus tunneling, magnetization minus tunneling. So now you no longer have twofold degeneracy. For the top block, you get one effective magnetization. For the bottom block, you get another effective magnetization. Right? This is we're now starting to get close to the sort of the heart of the issue. So again, even though we have tunneling and we're expecting the physics to be different, what we end up with is essentially two copies of Rashba plus magnetization. The only thing that's different is we don't get the bare magnetization, we get an effective magnetization. So if we had no tunneling between the surfaces, we would have Rashba, and then a magnetization on the top, the same magnetization on the bottom. If we have tunneling, we end up with Rashba, a certain magnetization on the top, a different magnetization on the bottom. The structure, however, is the same. Do we care that the effective magnetizations are different? So what do you think? Do we care or do we not care? Just take a guess. How many people think we care? How many people think we don't care? Let's see. All right. So let's take this situation, right? You have a topological insulator, thin film in which the tunneling is negligible, or an ultra-thin film. In both of them, the Hamiltonian consists of two blocks, right? A top block and a bottom block. So in both cases, it's Rashba plus some effective magnetization. The magnetization will open a gap in the spectrum. I can't remember what the last slide was, where I drew that Dirac cone. So this is what the cone looks like without a magnetization. You have a magnetization parallel to Z. So now you open up a gap in the center of the Dirac cone, and that gap will be proportional to the magnetization. So you do want the magnetization to be large, right? You certainly want it to be much larger than the temperature at which you're doing the experiment. And then you put your Fermi energy in the middle of the gap, right? So the valence band is full and the conduction band is empty. Right? So if the conduction band is empty and the Fermi energy is in the gap, there will not be a longitudinal conductivity. Right? The longitudinal conductivity is a Fermi surface effect. Right? It depends on the number density, right, of carriers in the conduction band. Right? There are no carriers in the conduction band here. So there will definitely be no sigma XX, because there is no Fermi surface to begin with, right? There's no bands intersecting the Fermi energy. So we have a Hamiltonian made up of two blocks, and we want to work out if there is an anomalous Hall effect. So there's no sigma XX, but there may be a sigma XY, right? So what is the contribution to sigma XY due to one block? So we've already worked this out. We actually calculated this in the second lecture yesterday. The block is Rashba plus some magnetization. The Berry curvature is exactly the same thing that we calculated for Rashba in yesterday's lecture. The only place where I was cheating yesterday, if you remember, is we had two bands, and I said I'm going to look at the bottom band, and I'm going to extend the wave vector to infinity, and that will give me E squared over 2h. And then we decided that it is, blatant cheating to extend the wave vector to infinity. However, here, it's not, mathematically it is cheating a little bit, but it's not cheating to extend the wave vector to infinity here, because there's nothing else beyond this, right? There's some technical reasons why You can't formally do this. Actually, to get the result correctly, you need a three-dimensional model, and you need to do a lot of formal maths. So Qi Xiaoliang has done it. So if you look up he has a paper from 2011. But still, you get the right result by doing this sort of simple procedure. You just extend the wave vector to infinity, and then one block will give you e squared over 2h. So the other block, right? The other block has minus the Rashba Hamiltonian, right? The other block will give you the opposite. So it will give you minus e squared over 2h. So then you'll think, hold on, this is not good. I get e squared over 2h from one part, minus e squared over 2h from the other part. This can't possibly be right. So then let's look at it. Let's look at the physical picture. So this is the top surface. The electric field is into the page, right? This is the top surface, which gives me a Hall effect in this direction, right? The bottom surface will give me a Hall effect in this direction, right? These surfaces, I haven't proved it, but these surfaces also have topological states, so current can flow around the sample. So these two Hall currents actually add up because there are different surfaces, and the current flows around the sample. Okay, so at the end of the day, they add up, and sigma xy is equal to e squared over h. So obviously this is easy to understand if the tunneling is 0, and we can simply think of the surfaces as being independent, right? And this e squared over h is the famous quantized anomalous Hall effect. So you will get it for a slab, right? You will also get it if there is tunneling between the top and the bottom surfaces, because the structure of the Hamiltonians is exactly the same. So the tunneling appears as a renormalization of the magnetization. So the magnetization, the effective magnetization on the top is not the same as the effective magnetization on the bottom. But we don't care because we're integrating over the entire filled valence band, and we are extending K from minus infinity to infinity. So the magnitude of this magnetization becomes irrelevant. And the interesting thing, which is something that I've been racking my brains over for the last 2 or 3 days, how to present this, right? Just think about it. So you get the same answer, but the mechanism cannot possibly be the same, right? For two independent surfaces, this makes sense, right? But when you get tunneling between the surfaces, obviously this picture makes no sense because the electrons live on both surfaces, right? So you can think of, a current from one block and a current from the other block, and they add up, but the mechanism for current flow within the sample has to be different. So this brings me to the sort of final picture on this topic, right? So the current flow in the system in which there is strong tunneling is related to an edge state, right? The demonstration for the edge state is in this Bible, and it's 1 page or half a page, and it's exactly the same algebra that I did to get the surface states. Instead of cutting it off at z is equal to 0, you cut it off at y is equal to 0. You get exactly the same thing. So, however, for the edge states to be well defined, right, we need the tunneling to be very strong. So we need the film to be very thin. We need it to be generally much smaller than 5 nanometers, so around 3 nanometers or less. Why do we need this? This is common sense, right? What is the main thing that you need to have in order to have an edge state? Sorry? Yes, to have an edge state, you need to have an edge, right? And if your system is like this, that doesn't have an edge. So there have been studies, actually Shen is one of the authors of this PRL 2011. You take a slab, right? You have some magnetization on the top and the bottom. on the sides of the slab, you still have some sort of edge states. You can only get it numerically, and they're very complicated, right? So before I move on to the final physical considerations, connecting to some of the stuff that we're doing in Fleet, right? I think this is a nice way to sum up the sort of relation between these topological quantities and physics. You take your Hamiltonian, you work out your topological quantities, and these give you the right answer, right? But to understand exactly, how current flows, so it's fairly simple in one case. It's, reasonably simple in the other case, right? But for cases in between, it's actually not so well defined. So we do understand the maths, but we don't completely understand the physics. Okay, so let me go back to the topic that I introduced in the first lecture, which is this topic of dissipation and whether things can flow without dissipation. Now, it's clear that if I make the longitudinal conductivity 0, right, there's no dissipation. I have a whole conductivity we just established on basic, grounds that doesn't dissipate energy. So is transport, if I make a structure like this, is transport completely dissipationless? So the answer is not entirely, because of at least two fundamental reasons. So what do I need in order to pass a current through a system? So I need to connect it to metallic leads, right? I need to connect electrodes to it, which means I need to connect this dissipationless paradise to the outside world. So really, the way you can think of it is, let's think of this entire structure, right, that I've talked about as an island, right? So this is your island. You have a lead here, a lead here. This lead has a slightly higher chemical potential. This lead has a slightly lower chemical potential. So you'll get some tunneling between the lead and the island. You get some transport inside the island, and then you get some tunneling back from the island onto the other lead. So first of all, the leads are metallic. They are certainly dissipative. They interact with phonons and all sorts of other things. Also, we have a potential difference across the sample. So you need a potential difference to get the electrons from here to here, right? So that energy obviously has to be dissipated when you go from the higher energy electrode to the slightly lower energy island, right? So quite often this is simply swept under the carpet, right? It's not so much, but it's generally swept under the carpet. So what we have proved in these last 3 lectures is there is no dissipation inside the island, right? But there is dissipation across the island, and there is dissipation in the leads. So one of our experts, so Jared Cole, is working very intensely on this at this very second. Now, likewise, so the way we control the number densities in these structures, I haven't shown anything about this because this is sort of semiconductor physics, but the way we control transistors, basically all semiconductor structures, is to put electrodes across, so an electrode on top of it, right? That electrode controls the number density. That's the main reason why semiconductors are so important, is you can tune the number density from 0 to some large value that is useful, right? So in principle, right, you have, let's say, an electrode, another electrode, and a system like an insulator between them. That's like a parallel plate capacitor, which, as you tune the number density, you're switching on and off. And switching this capacitor on and off actually costs a lot of energy, and it turns out that by far most of the energy that's dissipated in transistors comes from the gate. And imagining semiconductor technology or semi-metal, graphene, whatever technology without gates, I think right now is still inconceivable. There's also the issue of, so if we make a device, or I should say when we make a device, it should operate at room temperature. And so far I've been drawing figures of energy gaps, etc., etc. right? I haven't said how large these are. But the temperature in these experiments is typically, so I touched upon this yesterday, somebody asked a very good question about phonons. So the temperature here is of the order of millikelvin, or at best a few Kelvin, right? Right now the magnetizations are very small, right? So we will need the magnetization gap to be large. That's the second order of business. Before we do that, we need the bulk energy gap itself, right? Bismuth selenide is a topological insulator. It has a bulk gap, and this Dirac cone exists inside the bulk gap. For this system to be useful at room temperature, the bulk gap needs to be much larger than room temperature. So the system needs to be an insulator at room temperature. So the bulk gap of bismuth selenide is 0.3 eV, right? The bulk gap of silicon is 1.1 eV. Is silicon an insulator or a semiconductor? Right? It's a semiconductor. So that means that its bulk gap is not much larger than room temperature, not large, not large enough to be useful, right? So we will need to find a topological material that has very strong insulating properties, right? This is what is exciting a lot of people right now. So to summarize, right, on three-dimensional topological insulator, the surface states follow a Rashba-like dispersion. And for all intents and purposes, spin orbit here is everything. So there's no kinetic energy, so spin orbit sort of rules the day. Right? Each surface will give a quantum anomalous Hall effect. These add up to E squared over H. Now, you also have what's called a two-dimensional topological insulator, which is basically a thin film in which tunneling is very strong. You apply a sizable magnetization. That also exhibits a quantum anomalous Hall effect, which is explained by transport by certain edge states. So there's only one edge, one state on each edge, which circulates around the sample, and it can be transported without scattering, and then it's clear to see why this is dissipationless. The entire structure is not completely dissipationless because of some fundamental reasons, but it can still save quite a lot of energy. So this guy, Haizhou Lu, so he was actually, in the old days, he was a postdoc of Professor Shen. So he was responsible for quite a lot of their exciting work on topological insulators. So over these, to prepare these lectures, I've actually talked to him quite a bit. So thanks are in order. And thanks also to you for your patience. Thank you.